So in section 2.5, we're going to talk about tree diagrams, permutations, and combinations. So this is kind of like an additional section to section 2. So we're going to look at like a third way to kind of display probabilities and on top of Venn diagrams and the two-way tables. And then we'll talk about a very special type of probability using combinations and permutations. So a tree diagram is helpful if you're displaying the outcomes of an experiment that consists of a series of outcomes. So for example, YouTube is a popular destination on the internet for video sharing. 27% of adult internet users are 18 to 29. Another 45% are 30 to 49, and the remaining 28% are 50 and over. A study was done and found that 70% of internet users aged 18 to 29 have visited YouTube, 51% of those ages 30 to 49, and 26% of those 50 or older. So we're going to draw a tree diagram to represent the situation. So we're looking at two pieces of info here, age and YouTube. So the first thing we have is our population. So when we start with a tree diagram, we start with our population, which in this case is adults. So the first level of my tree diagram is going to be my age ranges. So we have 18 to 29-year-olds. We have 30 to 49-year-olds. And then we have over 50. We want to then label the branches with the probability that you fall within that category. So we know 27% are 18 to 29, so that's 0.27. We have 45% are 30 to 49, so that's 0.45. And then my remaining 28% over 50, so 0.28. Important thing here when we're talking about tree diagrams is anytime you draw a branch, those percentages, whatever you're drawing it from, have to add to 100. So 0.27, 0.45, and 0.28 add to 1. So I know it's a good probability model. From here, each of my age categories then get two branches because we're talking about whether or not you've visited YouTube. So you can visit YouTube, don't visit YouTube. And this is the same for all of them. Okay, now I want to add my probabilities. So we know of 18 to 29-year-olds, 70% of them have visited YouTube. So that's 0.70, which means my percent that don't, 0.30. For 30 to 49-year-olds, 51% have visited YouTube, so 0.51, which means 0.49 haven't. And then for our over 50, 0.26 have visited YouTube, which means 0.74 don't visit YouTube. So this is what a Venn diagram looks like. The way we then calculate probabilities from this is a little bit different. So suppose we select an adult internet user at random. What is the probability that this person is 18 to 29 and visits YouTube? So the way we do and probability is you multiply the branches together. So multiply branches. So I'm going to take the probability that you're 18 to 29, 0.27, and multiply it by the probability you visit YouTube, 0.70. And you get 0.189. Number 2 is what's a probability that any person has visited YouTube? So in this case, we aren't specifying which age category they're from, which means I need to find all of the probabilities associated with visiting YouTube. So that could be 18 to 29-year-olds, so 0.27 times 0.70. It could be 30 to 49-year-olds, which is 0.545 times 0.51. Or it could be over 50, so 0.28 times 0.26. So I have to count for any age category since I didn't specify to begin with. So you end up with 0.189 plus 0.2295 plus 0.0728. which gives us 0.4913. So 0.189, 0.2295, and 0.0728. So you add those all together and we get the total probability that any person has visited YouTube. Okay. Now we're going to talk about conditional probability. So given that a person has visited YouTube, what is the probability that he or she is aged 30 to 49? So when we're looking at conditional probability, so we're saying what's the probability you're 30 to 49 given you've visited YouTube. So when we break this down using the formula, our numerator is our probability you're 30 to 49 and visited YouTube. Our denominator is just the probability you have visited YouTube, which I'm going to abbreviate YT here just because it's easier. So we just found in our previous example the probability that you visit YouTube. So that's already found for us. My numerator is the probability that you're 30 to 49 and visited YouTube. So that in our previous example was the 0.45 times the 0.51. So I have 0.2295 over 0.4913. Which gives us 0.467. Let's look at a second example. So in a recent month, 88% of automobile drivers filled their vehicles with regular gasoline, 2% of purchases mid-grade, and the rest bought premium. Of those who bought regular gas, 28% paid with a credit card. Of those who bought mid-grade and premium, 34% and 42% respectively paid with a credit card. So we're going to do our tree diagram. So my population I'm looking is automobile drivers. So my first branches are the type of gas that was purchased. So you have regular, mid-grade, and premium. So for my probabilities, we have 0.88 for regular, 0.02 for mid-grade, and then 0.10 for premium. Each of those then get 2 branches where they used a credit card or not. So for those probabilities, we know regular was 28% that used a credit card, so 0.28, which means 0.72 did not. 34% of mid-grade, so 0.34, which means 0.66 did not. And then 0.42 for premium, which means 0.58 did not. So the first probability I want to find is the probability that a customer paid with a credit card. So remember, that is any of the three gases. So 0.88 times 0.28, so if they got regular and paid with a credit card, plus mid-grade, 0.02 times 0.34, and then for premium, 0.10 times 0.42. So we get 0.2464 plus 0.0068 plus 0.0042. So when I add those together, I get 0.2574. So for my conditional probability, I want to find that given a customer paid with a credit card, find the probability that she bought premium gas. So the probability you paid with a credit card, given you bought premium. Oh, oops, sorry, it's the other way around. Given you bought premium, probability you bought premium, given you paid with a credit card. So that's the probability you got premium and paid with a credit card, which is the 0.0042. And we already found the probability you paid with a credit card. So it's 0.0042 over 0.2574. I just realized I made a mistake on the previous problem. So this actually shouldn't be 0.0042. It should be 0.042. That's my bad. So 0.2464 plus 0.0068 plus 0.042 is going to be 0.2952. So now we're doing 0.042 divided by 0.2952. So we'll get 0.1423. So typically speaking, if you are doing a probability with a tree diagram, I prefer 3 to 4 decimal places. Never 2, just because you want to be as accurate as possible here. So we don't want to round really until the end. So keeping all of your decimals exact until the final answer, and then giving me 2 or 3 decimals. So last half of the notes, we're going to talk about permutations and combinations. So before we dive into that, we have to go talk about counting principles. So tree diagrams do tell us how many possible outcomes there are, and helps us to list those individual outcomes and organize the probabilities associated with each stage. So like in the previous example, I had 9 potential outcomes: regular credit, regular not, mid-grade credit, mid-grade not. So all of those combined gave me 9 total outcomes. However, sometimes we'll only be interested in the number of different outcomes created by a series of events, not necessarily the probability of a certain thing. So instead of having to list all of those out, there is a multiplication rule for counting. So if you have n possible outcomes for an event and m possible outcomes for a second event, then the total number of outcomes possible is the multiplication of those together. So in our previous example, 3 types of gas, 2 potential payment methods, which is 6. I know I said 9, but it's 6 potential outcomes. So in our example, There are 31 different sandwich options at McDonald's, not including breakfast. You have 4 different size options for fries, small, medium, large, and super. They don't do super size anymore. And then 4 different size options for drinks, which again, they don't do 4 anymore. How many different meals can be ordered from these options from McDonald's? So it doesn't just have to be 2, it could be 3 or 4. So you have your 31 different sandwich options times your 4 fries options times the 4 drink options, which again, there are not 4 anymore, but pretend there is. So there are 496 different meals. Based on that information. So you could get a different meal every day for at least a year at McDonald's if this information were accurate, which I don't believe it is because this is older information. So when we consider N items, sometimes we need to know the different number of ordered arrangements that are possible. Sometimes it didn't matter what you ordered first. Like in the example we just did with McDonald's, we didn't really care what order it came in, but sometimes order does matter. So there's a kind of a classic example of this where it's determining the number of different ways in which 5 people can be seated at a dinner table. So the first person has the choice of 5 seats. Once that person sits down, the second person only has 4 seats to choose from. The third person has 3 seats, and so on and so forth. So that multiplication pattern, not an unusual thing. So if I'm talking about it, I have 5 times 4 times 3 times 2, and then the last person has 1 seat, which means there are 120 different seating arrangements. Now, depending on what it is, that could be very time consuming to do all of that by hand. So we have something called a factorial in math. And the factorial is an exclamation point, and it basically represents taking however many options you have, and as they get removed, it does the math for you. So 5 factorial is the same as 5 times 4 times 3 times 2 times 1. A couple things, 0 factorial and 1 factorial, both equal 1. Just to kind of information there for you. Okay, so let's go back to that dinner party situation. So you invite 5 people, but you only have 3 chairs. So we want to know how many ways can 3 of the 5 people seat themselves in those chairs. So let's suppose our 5 people, we'll give them letters. We have A, B, C, D, and E. So those are our 5 people. So you could have that person A gets a seat, then person B, then person C. You could have that person B gets a seat, then E, then D. You could have person D, then A, then B. It just keeps going and going. So we want to know how many outcomes are there. So the first chair has 5 choices because you've got 5 people that can choose from that first chair. Your second chair then only has 4 choices because now there's only 4 people. And the third chair only has 3 choices. And I don't have to keep going at this point because now I'm out of chairs. So I only have to do 5 times 4 times 3 since there's only 3, which gives us 60 different arrangements. So if I think about this in terms of a formula, I had 5 times 4 times 3, all of my possible choices. So I had my 5 factorial, 5 times 4 times 3 times 2 times 1. But I 2 of those choices didn't get picked, so the 2 times 1. And then the 2's canceled and the 1's canceled. So this leads us to a formula for the number of ways to arrange in order n distinct objects taken r at a time. So depending on how many you have. So it's called a permutation, and we read it as NPR. So it ends up being n factorial, which are your total number of objects, over n minus r factorial. So you have to subtract how many you're actually choosing from it. And that is how you get your formula. Couple things here, because it is permutation, order does matter here. So for permutations, order matters. So if we're going to use our formula, so 5p3, I have 5 factorial over 5 minus 3 factorial, since I had 5 people but only 3 chairs, which ends up being 60. So there is a way to do this on your calculator. You're going to hit math. Then you're going to go over to, depending on your calculator, it's either PROB or PRB. And then it's number 2, which is NPR. And you can actually type it 5 and 3, and when you hit enter, you'll get 60. So in these examples that we've talked about, the order of the objects or people was taken into account, and the order was important. So what that meant was that if you considered a person sitting A, B, and C in chairs, that is separate from B, C, and A. So these are considered 2 separate events. For permutations. But then we have something where order does not matter. So if we were interested in different grouping of 5 people so that each group contains 3 people, the order of no concern, since all 3 are going to sit down. So that means all of the different ways to order people A, B, and C. So as long as it's those 3 people sitting, we consider those all the same event. So A, B, C, B, A, C, C, A, B, A, C, B, C, B, A, and B, C, A. These are all considered the same event. Because it's the same 3 people. So when that happens, we want to get rid of any of the repeats. So the way that formula works is that you have your 5 factorial, since you have those are your number of seats. And then you have the group of 3 people you want, 3 factorial, where you consider them all the same. And then the remaining 2 people who you don't consider the same, which gives you 10 combinations. So a lot fewer choices here if we consider any combination of the three letters being the exact same outcome. So the number of ways to arrange n objects taken r at a time for a combination is called NCR, and it is n factorial over r factorial times n minus r factorial. So in this case, order does not matter when you're looking at the number of arrangements. A couple of things when it comes to combinations versus permutations. The very first thing when you're trying to decide which one to use is to ask yourself if the order in the group of R objects is relevant. If it is, you use a permutation. If it doesn't, you use a combination. So combinations or permutations are good for determining the number of different outcomes in your sample space. We are going to talk about here in a second probabilities associated with them as well. So when it comes to combinations, we have with and without replacement, which we briefly talked about in chapter 3, and we're going to talk about more here in chapter 4. So sometimes the probability is affected based on what has already happened. So when that happens, it's without replacement. So this is another way to calculate conditional probability. So when a population element can be selected more than one time, we're sampling with replacement. And when a population element can be selected only one time, we are sampling without replacement. So for example, your dresser drawer is filled with 6 blue socks, 10 gray socks, and 4 black socks, unpaired and mixed up because you're a barbarian. One dark morning, you pulled 2 socks from the drawer without replacement because obviously you're going to wear them. What is the probability that both socks match? So there are 3 different occurrences for when the socks can match. It could be that the probability you have a blue sock and a blue sock. It could be the probability you get a gray sock and a gray sock. Or it could be the probability you get a black sock and a black sock. So there are 3 different ways that you could pick matching socks. So for my blue and blue, the probability the first sock is blue is 6 out of my total number of socks in my drawer, 20. My second probability is going to now change based on that first pick. So assuming my first sock is blue, there are no longer 6 blue socks in my drawer. There's only 5. And there are also no longer 20 socks, there are 19. Then for my 2 gray, so 10 out of 20 are gray. So that's my probability for my first sock. For my second sock, it would then be 9 out of 19. And then for my black socks, 4 out of 20 times 3 over 19. So when it comes to probability, so 6 times 5 is going to be 30. 20 times 19 is 380. Plus 90 over 380 plus 12 over 380. So 30 plus 90 plus 12 gives me 132 over 380, which is about 0.35. So there's only about a 35% chance that if you pick 2 socks, they actually end up matching. We will talk more about how to do probabilities with combinations and permutations as well. So this was just a very brief introduction into how a combination or permutation is calculated. We will in a later section talk about how to find probabilities with those, and we'll do a little bit with it on the assignment over this as well.